Good evening everyone. Welcome to the first live session of Mechanical Unit Operation course. Today we are discussing properties of particulate matter and how we classify them. Okay. So now I am sharing my screen. Can you someone please confirm that? Can you able to see my screen? Okay. Thank you for confirmation. Okay. Thank you for confirmation. So, as today is the first lecture, so I want to start with the basics of mechanical unit operation and what are the perks you will get after completing this course, and how this course is relevant to the career of the chemical engineer. So, first, this is all maybe know that this is the home page of this course, and the course already started from 25th of July and it will end up on 14th October, and the exam of this course will be on 30 October 2022. Now, today is the first lecture, so I want to give the brief introduction of the instructor. So instructor of this course is Professor Nand Kishore. He is a professor in Indian Institute of Technology, Guwahati. So this is the brief academic as well as research profile of himself. He completed his PhD from IIT Kanpur in 2008 and he is now full professor at IIT Guwahati. He has some achievement like Brunner Research Fellow. He was Brunner Research Fellow in UK from 2009 to 2011. He was a visiting researcher in the Department of Chemical Process Engineering in UK in 2016. He also received many research awards and many awards. Out of that, one is 2000 Young Scientist Research Award in 2016, EI Young Engineer Award in 2015, Young Scientist Research Grant from SERB DST Government of India. So today is the first day, so I also want to give short introduction of myself, and you can, because you can take the note of this, and in future if you want to communicate with me, then you can use this mail ID ch19d752@smail.iitm.ac.in. I am PhD scholar in Chemical Engineering Department in Indian Institute of Technology, Madras. So I know that many of from you already have done the NPTEL course and they all know how it goes and what is the criteria for the certification, and how exam is conducted. So the main motto of the NPTEL is learning is always free. So that's why anyone can learn by using this course without giving any fees. But if you want the certification for this course, then there will be one entrance exam. It will be optional, but if you want to give, then you need to pay the exam fee of 1000 rupees. For this particular course, date and time of exam is on 38 October 2022, and exam will be conducted into 2 sessions. Now, what are the criteria for this course to get certification? So there are 2 parts of this course. One is an assignment and another is an end exam. So 25% of the total score will be covered from the assignment score, and another 75% will be from end exam score. So the total score will be the summation of the both the score. Now, so this also maybe all know, but for this particular course, you if you want to get certificate, then average assignment score will be greater than or equal to 10 out of 25, and exam score will be greater than equal to 30 out of 75, and either of the criteria is not met, then you will not get the certificate even if your final score is more than 30. Okay, I just check that recording is going well or not, because it is important. Now, so many of you already visited the whole structure of the course, but I want to brief you again. that we will in this course we will discuss about the mechanical unit operations. So mechanical unit operation is also divided into the two different areas. One is the solid uh, separation, another is a solid fluid separation. So in the solid separation, first we will start with the introduction of particular sizes and shapes. Another week, in the second week, we will discuss about the screening. Third week is all about the size reduction. Then fourth week, we will discuss storage and conveying of bulk solids. In the fifth week, size enhancement. And week 6 will be the discussion on flow past flux bodies. And week 7 we will discuss the flow through tech and real estate. Week 8 is all about the filtration. So and then week 9 is cross flow filtration and membrane separation, and gravity sedimentation, centrifugal separation, and flotation. So the previous part is all about the solid and then solid fluid interaction will be discussed. So this is all about the mechanical fluid operation, mechanical unit operation course. Okay, so now books and reference already been discussed by professor, but you also make a note of all the important book. So we will discuss in some topics from the unit operation of particulate solids, theory and practice from E. Ortega. And the most important book of this subject is Unit Operation of Chemical Engineering, which is from W.L. McCabe and J. Smith. And the Coulson and Research on Chemical Engineering volume is second volume we also use for the little bit discussion on the solid fluid interaction. Now, so introduction of the particulate solid. This is the name of the first lecture. So here we will discuss about the particulate solid, or if you want to give in this you other name, then it will be solid particles. Okay, so what we need to understand about this and what are the characteristics of this particulate solid, how we will use for the separation purpose, and what are the physical laws we need to follow. So we'll start with the first. Professor started this whole session from starting with what is the chemical engineering, what is the role of chemical engineering in industry. So that is very important and interesting topic. So I want to also touch briefly to that topic. So first is what is the chemical engineering. So chemical engineering is all about we need to convert the raw material into the useful product. So the raw material conversion or separation into useful products is known as a chemical engineering. Now, what are the duties and what are the responsibilities of the chemical engineer? So mainly there are many duties, but if we roughly say, then one is the develop, design, and engineer complex process as well as equipment. We need to not only develop process, but we need to develop and design equipment also for that particular process. We need to select the raw materials according to our need. We need to operate plants with safety, with the safety, efficiency, and economically. So all the techno-economical aspects one must chemical engineer should keep it in his mind. Check whether product meets the requirement. So the all manufacturing industry is boils down that for the quality of the product. So we need to always make sure that our whatever product we are manufacturing, which is at particular standard quality level, and it is meeting our requirements. Now we will turn whole discussion to the unit operation. So although this is a tutorial lecture, but I want to give you because as a first week there is no much examples and no much numericals you need to solve, but you need to understand the overall idea of why we need to study this course, why it is related to the chemical engineering, and how and when we can use this course in our real life. So because you all of these consider all of these facts, we need to understand a little bit brief introduction of this course and its application also. Now, how it is correlated with our chemical plants, we will see now. So, chemical plants consist of mainly uh, uh, three things. Wait, I want to check that recording is going on or not. Okay, so chemical plant consists of three steps. One is the upstream process, another is a reaction, the third is a downstream process. Chemical engineering is not all about the reaction of the any process. We need to take care of the upstream process also. So before raw material selection and after that getting the raw material, we need to pre-process the raw material also. For pre-processing a raw material, we have to use some operation like crushing, grinding, washing, filtration, drying, mixing, etc. And then pre-processed raw material will go into the reaction phase. In the reaction step, we are some examples are oxygenation, hydrogenation, polymerization. This kind of reaction we will take care. We have to taken care of in terms of generating the products. And then after completion of the reaction, we need to post-process the products to get the final output. So for that, we are using some separation unit operation like distillation, evaporation, extraction. These all are most of them are you will learn in the mass transfer operation also. So this is all about the how chemical plant works. Now, what is a unit operation? So unit operation is always described as a physical or mechanical procedure. Okay, so unit operation, there is no any chemical process is going on. So we can use physical or and mechanical. So we can use mechanical means, mechanical forces, mechanical method to solve our purpose, or we are just using the any physical process uh, which can change the shape of our products and shape of our materials, which are always running in parallel to our chemical reaction. So always chemical reaction is always going on, but these physical and mechanical operations are also taking place along with them. That is why they are also known as a unit operation or mechanical unit operation, which is only we will see what it consists in the upcoming slides. So this is a diagram of chemical engineering which we just discussed. So chemical engineering is all about unit operation and unit process. And in unit operation there are four main unit operation, and out of these three unit operation you will learn very much detail in other courses, and that are also very important to interpret all the operations which we are performing now. So fluid flow, heat transfer and mass transfer, these three operations will be always important in order to understand the whole basics of chemical engineering. But if you want to discuss about the mechanical operation, then mechanical operation, it does not require the all the core processes and core ideas of the chemical engineering and but we have to understand all the basic laws of physics, basic laws of mechanical engineering, you can say, to understand what are the mechanical operations we can perform, which can change the properties of solid, and then we can easily separate solid from solid, gas from solid from liquid. This kind of separation and this kind of property enhancement will be done with the help of this mechanical operation. So this is all about the introduction of mechanical operation. Now we will discuss how it is how we will use them. So the mechanical unit operations are the operations which are purely based on physical or mechanical forces, such as, so mainly these three forces are always used when we are talking about the mechanical unit operation or mechanics of unit operation. So gravitational force, centrifugal force, and mechanical or kinetic forces arising from flow. Whenever we are using the gas liquid or solid liquid materials, then there are always we need to understand about the kinetics and mechanical forces, like such as we need to understand how the shear force, viscosity, and then different laws of physics need to be followed or not. Then, if we talk about the classification of the mechanical unit operation, then it can be classified based on the phases. As at the time of initial course uh, description, I told you that we need to classify the mechanical unit operation in the basis of phases. So in a particular lecture also we will classify our whole unit operation or mechanical unit operation into the two type of operation. One is a solid operation and another is a solid fluid operation. Sorry. Okay. So solid operation which only solid and both the phase are in the solid form. So we are performing the operations like crushing, grinding, compaction, cutting, storage and transport of the solid. While the another class of the operations is is solid fluid operations, in which we need to understand the basic phenomena of the separation of solid out of fluid. So it will include infiltration, sedimentation, centrifugation, separation, and different types of unit operation we need to understand in that. So one is a solid operation, another is a solid fluid operation. Okay. Okay. Time to decide. Anyway, we will go over particle in solid system can be separated according to. Now how can we separate the solid system particles? So there are two ways to separate it out. One is on the basis of size and another is a material type. So on the basis of size we need to for an example we need to separate the solid on the basis of size, like coarse particle and settling, like sieving. Screening is the main when we are talking about the size. So screening is the main operation to separate it out, and another is a material type. So on the basis of properties of the material, suppose you have two different kind of solid, but one solid can be dissolved into the organic solvent and another solid can be dissolved into the aqueous solvent. So on the basis of this dissolution process also you can separate the material. So that is also one way of separate the materials. And there are many properties, not only solubility. If you talk about the magnetic separation, then some materials can be easily attracted towards the magnetic force, so you can use that the same phenomena over there. Electric forces also can use. Flotation material and bleaching, some of them operation we can use to separate the solid system using this kind of size and material type of process. So one is the size we need to understand, another is a material type. So material type is in another word properties of materials. Okay. So now this is all about the solid system. Now I want to just draw your attention towards the powder and particle technology. So what does that mean? Already professor explained why we required to develop the powder and particle technology, and what is the output of that particular course. So main thing is in early 20th century up to mid 20th century, no one is talking about the bulk and solid state matter. Although fluid and other operation including fluid materials, fluid particle, operation with fluid is very well known. Fluid flow phenomena is started very early, but no one is discussed about the solid. So neglected, solid is neglected. So then in the after industrial revolution and after the mid 20th century, like after the second world war, Germany start the terminology powder technology, and it also come as an academic discipline. So we are just learning some brief operations on the powder technology, but there is whole discipline which is working on the powder technology. and characteristics, properties, and how can we use and enhance the properties of this powder. Now, so what is the powder technology? So powder particle technology is a branch of engineering which dealing with the systematic study of particulate matters, which are either in the dry form or it's in a suspended form. So that's how whole powder technology is working. So although we are not going into much detail of this, but how this solid mechanical unit operation started to build their own importance, it is very important to understand. Please don't mind my this handwriting because I am not there very much used to by using this digital board, so that's why. But if you don't able to read any of my word, then you can ask me directly that what am I trying to explain. So till now it's a conceptual part only. I want to go through little bit theoretical part so you can understand why it is required and what we are going to study. Now we started with the particle characteristics. Okay, so most important thing is particle characteristics are important, and it is based on the three property of the particle. One is a size, another is a shape, and third is a density. You always remember. So first we need to understand what are the particles and size of the particles, because every particle has a different size. So some are, if you can talk about, some are in the rectangle size, some are in the sphere, some we are not every time we are fixing the size, we are getting the particular regular size of particle, but these are the different kinds of size. Some of the particle cylinder. Most of the time particle has this irregular size, so we need to convert this irregular size into the some measurable size phenomena, where we can get some diameter information or some volume and surface area information from it. So from irregular we can't do anything, so we need to convert this irregular size particle into the some regular shape. So we will discuss it in later. So now another part is the shape of the particle is we need to understand. These are the size is also not only the shape wise, but it is also like big particles, small particles. The same, everything needs to be covered in the size. But if we talk about the shape, then there are very different shape, as I already mentioned here. Different kind of shapes are there. If you talk about the packing material, then packing material mostly cylinder in the cylinder shapes, and sometimes in the irregular shapes are there. So that's why this is the shape is also important phenomena. And density, always which is the material which we are using to form our particles, that will accommodate density is accommodated into that particular material characteristic. Now size. So powder or particle material is also characterized on the basis of size. So from the size also we can clearly say that okay, this material is this powder is a coarse powder, this powder is a fine powder, this powder is a medium size powder. So mainly these three uh, different types of powder materials are there, and out of it, so roughly we want to understand, then coarse particles are in the measure in the measurement of centimeters and millimeters, while fine particle always measure in terms of the screen size, and very fine particle is in micrometer and nanometers. Out of these three, another one more classification we can consider, that is ultra fine particles, which is measured in terms of the surface area per unit mass. So when we are going for the very fine materials or nanoparticles and nanomaterials, then the size distribution is measured on the basis of surface area per unit mass, which is also which is in have a unit of meter square per gram. Now, representing the size of irregular particles. Now, how can we represent irregular particle into the some form? So, as we discussed now, that this kind of any irregular particle is there. If you want to understand it and we want to study more, then how can we take care of it using any kind of phenomena. So here we are understanding that we always use different kind of diameter, and that diameter is always equivalent to a sphere. So most of the time we follow the spherical geometry to represent our irregular size particle. The main reason in that obviously sphere has a very minimum surface area, and the most of the particles we can easily converted into the uh, spherical. We can easily convert into the spherical whatever we are using to some equations for the spherical particle. We can directly easily convert all kind of shapes into them. So in that we are representing diameters on in the basis of different applications. Like here you can see the volume diameter is there, which is we are comparing with the sphere volume of sphere. There is a surface diameter. For getting the surface diameter, we need to come equivalent sphere surface diameter. We need to uh, consider. Now, depending on the application, like volume diameter maybe can be used to the PET column, PET material, or some application where volume really important. The surface area really important. Surface area is also like if you want to absorption column, and there if you want to use some particles for increasing the enhancement of mass and mass transfer surface. Then drag diameter, which is a resistance to motion in the same fluid at the velocity. So we all know that we have performed some experiment in which we are checking the resistance of solid particle into the fluid medium. So in that kind of application like bubble column and so, we can go for drag diameter, Stokes diameter. If the same uh, fluid and solid particle motion will be done in lower Reynolds number, so we can use the Stokes diameter. Then free falling diameter, the free falling in the same liquid kind of thing. Sieve diameter. Now whenever you are using the sieving, any sieve for screening the particle, then whatever we are using the diameter of sieves, hole between the sieves is the mass size, and how we will discuss into upcoming lectures. Our professor will be discussed in detail, and we will solve some example on the basis of that. So that is known as a sieve diameter. So these are different diameters we need to understand for representing the irregular particles. Now, so this is all about the we can physically control over the different kind of shapes and diameters. But if you want to measure the very accurate amount of measurement of any particular particle, then we will follow the statistical diameters. So statistical diameter generally we will follow to uh, measure the diameter or particular particle in a very reliable manner, in a with very highest accuracy and precision. So for that we will use the linear dimension, which is a parallel to a fixed dimension. So how we can do that? So like some microscope, different kind of microscope for understanding the diameters that is using with different kind of statistical diameter. So there are many different methods here. So I am just listing out 3 or 4 which is discussed by the professor. One is the Farrett's diameter, which is nothing but the distance between the two tangents on opposite side of the particle. So whatever the opposite side, we are just plotting the tangents, and diameter of that particle is a Farrett's diameter. Then Martin's diameter, length of the line which bisects the image, which is the bisecting the whole particle into the image of the particle into 2 parts. Same as the Sear diameter, with particle with obtained with an image searing eyepieces. So it is searing the whole uh, image, and that the maximum core diameter, which is the maximum length of the which will be cover the maximum length. Okay, so this is all about the statistical diameter, which we are not generally using in the industrial scale, but yeah, if you want to go for a research in a very specific particle size, like we need to understand the catalyst and all, or the platinum and gold nanoparticles, some kind of this kind of solid particle we need to understand for some research purpose, and for the characteristics of it we will go for this statistical diameter. Otherwise in industrial scale it is very it is not possible to do this lengthy study for a single particle study, because we have bulk of solid particles which is also different size. Now, whenever this all about the size calculation, we always consider the sphere. So, when the diameter will be mostly sphere volume equivalent diameter. So, that's why I am representing this table over here. So, in that, for different kind of shapes, what is the sphere volume equivalent diameter will be there. So, sphere volume equivalent diameter is used for the some amount of some operations where it required to understand what is the volume of our material we consume. So here in that I am deliberately giving the this I am again revisiting this table of the sphere volume equivalent diameter, because many of your assignment questions is directly related to this. Okay, so you need to understand first this. Whenever we talk about the sphere, the volume of sphere is, if you always remember about in terms of radius, then 4 by 3 pi r cube. And if you talk about if you substitute the value of r as a d by 2, then sphere volume is pi d cube by pi d cube by 6. Now this is our standard we consider as a sphere volume, and then all the different kind of shapes sizes which we are considering, we are just equating with to this sphere volume for getting the what is the particle volume in terms of sphere volume equivalent, or what is a obviously particle equivalent diameter in terms of sphere. So same if we talk about this cylinders. So if we consider the cylinder in L equal to D, and for cylinder we know that pi r square L, and there are L equal to D, and if we substitute D also, so D by 2, then pi d cube by 4. Okay, so now if we want to calculate the sphere volume equivalent diameter for this, so pi d cube by 4, which is pi dp cube by 6. So now dt is equal to 3 by 2. We need to take the cubic root of d. So this is basic different properties when we diameters when we consider in the different shapes with sphere. And so this is where I just discussed the L equal to D cylinder. Now same you can go for the cubes, D cube. You need to just do the calculation and you will get D equal to D. Now if we talk about the hemisphere, so hemisphere is the half sphere. Okay, and there is some example in the assignment which is based on the hemisphere. So how can we calculate the volume of hemisphere? So volume of the hemisphere is equal to, when we are talking about the sphere, 4 by 3 pi r cube, for hemisphere 2 by 3 pi r cube. This is a small change which we need to consider. And where if we talk about in terms of the diameter, then pi d cube by 12. So if we compare it with pi dp cube by 6, sphere equivalent diameter, then dp is equal to somewhere around 0.7937. You can easily do by the calculator. So this kind of, and then if you talk about the tetrahedron and octahedron, so there is one question which is present in there in assignment, which is based on the tetrahedron and octahedron. So I will not give you the answer of any particular kind of question, but tetrahedron you can consider as this prism kind of shape, and here all the sides are equivalent of A, or you can say S. So what is the area, what is the volume? So volume is equal to, if we want to consider, then S cube root 2, this is there in geometry, you maybe probably all know about it. So S cube root 2 divided by 12. So that's how that's how we are using this as a volume. And as you can understand, if we talk about the octahedron, then octahedron has a 8 sides, different sides. So this is why tetrahedron has a 4 sides. And now we need to use the volume is equal to for the octahedron root 2, and uh, now we need to divide it by 4, so it is converted into the 3. Those 4 more sides we include. So this is a two different octahedron and tetrahedron volume of particle equation. Now from this volume you will get, the question is about surface area. Now you need to consider, you need to calculate which has a very if the both volume are same, so which shape has high surface area. So you can easily compare it out, and then you can understand by comparing them both. Okay, now this is all about the particle size. Now if we want to discuss about the particle shape, then the main thing is we need to understand that particle doesn't have any regular shape. So that's why we need to consider the every irregular particle into particular shape. And here also we are using spheres. So from the sphere we will use the quantity known as a sphericity. So as in layman language, if we talk about what is the sphericity, then anyone can understand that sphericity is any irregular particle is how much near to the sphere. So if we want to understand that any particle is how much, if it is the sphericity of the any particle is 1, then we can say that okay, this particle is exactly look like a sphere. But if the sphericity is like 50%, 0.5, then we can say it's only half same as a sphere. So this is in the normal language you can say what is a sphericity. But if you want to exact definition, so sphericity is always represented by phi s. So in that your particle has some volume Vp, and its same volume of sphere we need to consider, and that surface area of that sphere, surface area of your sphere is the same volume of your volume of particle. Whatever your particle which you want to understand, the same volume of sphere you need to take care. So here, and the surface area of your particle, you need to consider this both things for the calculating the sphericity. So suppose you have 10 centimeter cube of any irregular particle, then you need to take the same volume of sphere and then calculate its surface area, and then you have to calculate the surface area of your irregular particle, and after that by taking the ratio you will at the end get sphericity. So this is a simple definition of the sphericity. Now in this Vp is here, how can we this is we said theoretical, but how it will represent. So for the phi s, we will so volume of particle is denoted by the Vp, surface area of the particle is denoted by the Sp. Now diameter of the particle, so same diameter of particle of which is equivalent diameter of the sphere. So equivalent diameter of sphere we have to denote like pi by 6. We know the volume of sphere dp cube, pi by 6 dp cube, and then surface area of the sphere of diameter dp. Now surface area of sphere, so sphere has surface area which is denoted by dp square, which you all know. Now here instead of this dp we need to use we need to use this equation, and the value of dp will be substituted from here, and at the end the value of sp we will get 6 Vp by dp. So this is how you will get the surface area of surface area of sphere. So now in the end Okay, so in the end you will denote your surface area of sphere divided by surface area of particle. Surface area of sphere you will denote by 6 by dp, and surface area of particle is sp. So this is how, this is the equation of the sphericity which we will use for understanding the different kind of shape and how much it sphericity is. So in this, sometimes this dp, which is also known as equivalent diameter, which is taken as a nominal diameter. To calculate equivalent diameter, dp is taken as a nominal diameter based on the screen analysis or microscopic analysis. So in the microscopic analysis and screen analysis, always diameter is denoted as a nominal diameter. So that's why we can consider it as a nominal diameter also. Now, what is the importance of sphericity? As I already discussed, that in order to design the processes, design the unit operations, you need to take care of the different physical properties of the materials. So for that, our particles are very much different in the different shapes and size. Like this spherical particles, we are using some sand particles, silica, then it is almost spherical. Some maybe are rounded, and some packing if you are using that are angular. Spongy material if you are using that has an irregular shape. Some metal are in shape of flaky. Some racing rings in some different packings are in the cylindrical shape. Some are in the cubic shapes. So for all of these materials, what is the sphericity we need to understand? If the sphericity is very much high, then we can consider there's a high sphericite materials, and the sphericity is very low. So if sphericity is low, then we can predict that if no one will give you the shape of the particle, but if someone says that particle of sphericity is 0.1, 0.2, 0.3, so like that, if sphericity is very much low, then you can understand that okay, this particle is obviously not at all sphere. It has some angles in it. It has some rounded and some sub-rounded sides. So that's why sometimes you need to understand which kind of material is well suitable for your operation, and at the end for your application also. So according to that, you need to understand that what are the properties of it, and from the properties you will at the end design the whole unit operation. Okay, so for all this reason we need to understand sphericity in very much detail. So these are again different shapes which are available, and which are the different terms which is given to those kind of shapes. Okay. Now for the sphericity, this is one example. Even though professors also calculate the sphericity directly, and in assignment also there are various questions regarding the calculation of the sphericity. So we will see some basic examples how to calculate sphericity. So we are calculating the sphericity of for this. If anyone has any question at the end, you can ask, or you can ask in the chat box. Better I am suggesting that you can ask at the end, and now just focus on the whatever things are going on in the screen. So first is for hemisphere, we need to understand the volume of particles. So as we know that volume of the particle for hemisphere is pi d cube by 12. We already see it, and now its surface area if we consider, and for the hemisphere we already always prefer 3 surface, so 3 pi r square, and if we convert it into the diameter terms, then 3 pi d square by 4. Now equivalent diameter, it is a very easy thing which we always completed. We need to just equate this diameter with diameter of sphere, so pi dp cube by 6, and then you will get dp value of dp in terms of d. So at the end all in terms of d is equal, so you can easily calculate the value of sphericity. Now you all know that sphericity doesn't have any doesn't have any unit, because everything in above and below is the same. So at the end you will get only value. So 6 Vp is 6 into pi d cube by 12 Vp 0.7937. Pardon for my handwriting. Vp into Sp. Okay, now Sp is 3 pi t square by 4. So at the end you will get the value of price, which is near about 0.840. Okay, so this is some simple example. If you want to see some more example, then the same example of cylinder we can consider. So there is one assignment question is also there, and there is a cylinder example, and we start with the volume. Vp is equal to pi by 4 d square L. This is the volume of the cylinder. Then area Sp is equal to pi dl plus pi d square by 2. And equivalent diameter. So for equivalent diameter dp, it is around dp cube, and then we need to just compute accordingly. But here I am directly taking the cube root, so dp pi d square by 4 n. Okay, same one Vp divided by pi by 6. Okay, so if we again solve this, then 3, and here 3 by 2 and d square n. Other things will be cancelled. Now, so the same, what is the value of phi? So for the phi we need to just put all the value which we discovered, that 1 by 6 pi by 4 d square L and the dp in the denominator plus pi by 2 d square. Now this is equation of the phi. Now there may be many cases, like L is equal to D. If you consider L is equal to D, then here put value of L is equal to D. So if you put D, then d pi by 4 d cube. So Vp is equal to pi by 4 d cube. Sp, same Sp is equal to pi d square plus pi d square by 2. So 3 pi d square by 2, and dp is equal to, if you talk about the things, then 3 d, okay, d cube is okay, and phi p will be 6 into pi by 4 6, okay, pi by 4 d cube and 3 by 2 d 3 by 2 pi d square. For this, if I remember, L equal to D, it's come around 87 something. We will see in the table. There is one table also. If we consider L equal to D by 2, then same thing we need to consider, but here D by 2 is Vp is equal to pi d cube by 8. Then Sp, as you understand, pi d by 2, so pi d square by 2 plus pi d square by 2, it's pi d. So Sp is pi d square, and something like that. At the end, pi p you will get around 0.825. So this is how you will take care of the calculation of this sphericity, and some of the examples are already asked in your assignment questions. But I want to discuss about the overall how to calculate this. In this table, almost all main important shapes are mentioned. Like this, for the sphere, we know its sphericity will be 1. We talk about the short cylinders, then this L is equal to D. If we consider, we okay 0.8474, we just take 0.87. if we consider short cubes, then L equal to d cube, then surface area of the particle is SP will be 6d square. Same we need to consider, we need to find first volume of the particle, then surface area of the particle, and at the end we need to equate them with the what you can say sphere particle, sphere equivalent diameter. So in the diameter and all this value we need to put into the equation of the sphericity 650. Again you directly you can remember this equation also, 650 by SPTP. It's very easy to understand, not much difficult. And then you can find the sphericity of any kind of particle. Even for the hemisphere, as we directly we just calculate 0.840, and for tetrahedron and octahedron also you can find the sphericity. Now sphericity has a range from, it's not like that it's always in the range of 0.6 to 0.8. For some materials like for some materials the sphericity will be very low, which is only 0.28, 0.3, 0.4, that also. So for that kind of materials the application is totally different than the high risk spherical materials. So if you want to use that kind of material, it will be very well suited into the catalysis process. Now we will go for the next one example, which is very famous example in this kind of study for calculating the sphericity, which is the racing rings. So if anyone is not aware about the racing rings, then for this calculation of the racing rings is what is the racing rings? And racing rings are the cylindrical particles, it's not like this. There is a one big cylinder, it's hollow from inside. So this material is only, as you can see, this much thickness is there. That is also only the part of the metal or any. It is also made out of the plastic, your silica, your metal from different mills. And in the industry, and here we are dealing with the PEC column. So for the packing, this is used as a unstructured packing or random packing. The racing ring is used, and we are considering one example in it. We are considering the value of the inner diameter of racing rings is 0.25. It is 0.25 times of outer diameter, and whatever the length of the rings is, it is equivalent to the outer diameter. Now for this we need to consider the different surface area. So for the inner surface area we can consider the we can consider the inner surface area with the help of pi. Actually for cylinder we are using pi dl. So for the inner we are using pi dl. For outer we are using pi dol, and our base surface area, which is only the material which is metal part of it. So it is pi, and base is circle in the shape. So pi do square by 4 minus pi di square by 4. So this is the how base surface area is calculated. Now in order to consider the surface area, total surface area, we have to do the summation of all the surface area. And as you can see here, we perform the summation, and here we put the substitute the value of dO is equal to L and di is equal to 0.25 dO, and again we will get the total surface area 1.719 pi dO square. Then volume of the ring, so volume is also you can consider the volume C, and cylinder volume is pi d square 4 by L. Now here you need to consider di square and dO square. Sorry, di square and dO square difference. So at the end you will get the value of 0.23445. Now volume, you already get the volume, surface area. Now we focus on the diameter. And diameter is pi dp cube by 6, which is the sphere diameter, which will equivalent to the volume of the ring, and at the end we will get dp is equal to 1.406 do. And at the end you just substitute all the values into the sphericity formula, and then you will get the sphericity is around 0.582. So this is particularly is about where inner diameter is 0.25% of the outer diameter. But you have one example in the assignment where you need to do the calculation for the di is equal to 0.75 do. So you can easily do. I think you just need to replace the values and understand how the calculation things work on. Now I just want to tell you that this is the conventionally people are using lacing rings in the packing materials. Now according to the application, according to the more specific operation, lacing rings will be replaced with the racing rings, ball ring, and then different types of saddle and interlock packing, ball packing, honeycomb packing. Honeycomb may be the structure packing, but now everywhere this lacing ring is not going to use. According to the very difficult separation, the shape of the material is also very much difficult. But don't worry, no, I think in your assignments only questions is on the lacing rings only. But if you can easily do the question if it will come on the racing ring or somewhere, if you have this all the diameter and the length with you, you can easily do the calculation for the other materials also, although it will require more time. That's it. Now we want to discuss about the shape, size, and the third thing is density. So now density. So density basically is classified in three different density. One is true density, another is density is how the total volume is you can classify the density according to the how total volume is measured for your particle. So one is a true particle density, another is apparent particle density, and the third one is effective particle density. So I just want to give you one example. Suppose this is my particle size. So just take care of, just consider this as your particle size. Here some pores are there, so which is see-through, like whole material is degraded, it has a kind of design, so pores are see-through, and we have another pores where it is a partially filled, like it is not fully full pore, but it is like you can say some rubbing, because of rubbing or because of some different operation, that kind of pores will be generated. So true density is the represent the mass of particle provided by its volume excluding open and closed pores. So here you can say that this yellow one is the closed pores. Suppose it is closed pores, and this blue one is the open pores. So when we are not considering this open and closed pore, then the density will be true density. It is the actual density of the material. But if you consider the mass density of the particle excluding only the open pores, okay, so then it is known as a apparent density. And you consider effective density when you are consider density by including both open and closed, everything you include, and it is known as a effective density. Okay, so this is all about density, and all obviously depending on the dimension and all three densities are different from bulk density of powder and particulate matter. So now this is all about the first lecture. I already took most of the whole hour, so any questions I just want to see. Okay, so there is one question which is sir, can you please tell me about the sphericity of the small particle and large particle of the same size? Will it be the same? Yeah, definitely. They are very interesting questions. So whenever we are consider the different shape, different size of the particles, whether it is a small size or large size. So sphericity is we consider for the shape of the particle. So if I have then cylinder which has this dimension, in a 5 cylinder which has very large dimension. But if I want to consider the sphericity, then 6 pp by spdp. Here at the end sphericity is unitless property. Okay, and we just take the ratio, and if this L and this D, suppose this is 4L and 4D, so at the end the ratio and all, if you consider all the constant value, if it are same, then it will be cut it down, and at the end you will get the same sphericity. So sphericity is not depend on size. Okay, independent of size. Okay, so you need to consider this thing always. And this week I am just closing the today lecture. No more question are there. And again, with this beautiful thought from the Maurice Wilkins, that the general rule is, if you are not prepared to make a mistake, you are not going to make much progress. So you always have to be always prepared to take a mistake. If it is mistake is there, you need to consider it, and whenever it with the help of these mistakes and past experience, you will learn and you will go further your progress. So this week I want to stop sharing my screen. Okay, and then just want to thank you all for be with me. And if you have any questions in future, you can contact me on my mail ID and in the subsequent lectures. Okay, thank you.